For this demonstration, I have set up the Zedboard FPGA. First of all, we have to make sure that the configuration of the switches are well placed for reading from the SD card that is below the FMC imagined expansion card. That expansion card is connected through HDMI to a cam. This one is the Sony HDR-30V. So first we have to start the system by turning it on. This will take a while since it's charging all the system from the SD card to the microprocessor. This is all done by a FSBL, that stands for First System Bootloader. Have to speed up the video just to make sure we don't have to wait much longer. Here at this point it's starting to charge all the drivers, for instance the handling of the mouse, or all kind of drivers. It's starting to set up all the commands for the graphic unit interface. So as you can see, it starts perfectly, and we start by hitting from the test pattern generator. That is a IP core created by Xilinx. As you can see, that can bring us some useful features for testing all the system. There in the bottom right we have two graphics that can show us the percents of usage of the CPUs, for instance for this Sobel filter processed by software. As you can see, that one of the microprocessors goes to 100%, and when it goes to hardware acceleration it goes down to 0, even though the boost rise up, but it's not over the 80%, so we can implement another IP core more complicated for image processing. So now if we put the start mode video image captured by the camera, we can see that from the software the processing system is quite slow. It rises up also to to the 100% of usage of the CPU, so it overflows. And if we put it on the hardware system, doing the hardware acceleration with the FPGA, we can see it's in real time. The input video is captured by the camera by 60 frames per second, and the output is also 60 frames per second. Here we have a little lag caused by the whole system, not regarding of the correct processing. And the resolution for the image is 1920 by 1080. So now we can get out from the graphic unit interface and access for making all the commands for the UART. So as we can see here, it starts perfectly, and well, the system is exactly the same. The only difference is the input of the commands. So as we can see, the results are exactly the same. The commands are given to the UART by the keyboard, managed by the operating system through the Linux kernel. And well, right now, as you can see, this is the input of the video with the software processing, just like exactly the same that we had in the graphic unit interface. So, and this one colored with red is exactly the one with the hardware acceleration done by the FPGA. So just for going out, we only have to hit 0 and we can turn off the card. This is another demonstration, but for a posterized filter. It's often done by photography, for instance. So just like in the other system, it's connected by HDMI to the camera. We have to turn on the system, so this takes a little bit, and then it starts all the system, but from the SD card to the microprocessor. So this kernel is the normal kernel of operating system of Linux. Later I will show another one done by VITA-2000, that is an operating system from Linux developed by Xilinx. So here we have to start the command center or the graphic unit interface. In this case, as you can see, the commands are exactly the same as in Linux. We have cd, for instance, for changing a directory. So we have to go to the main car to search for the program that we have developed. That is a program that is a point AELF, sorry. So that is the one that starts all the system. It's in charge of all the controlling of the commands, for instance, given by the UART. Now we turn on the camera, and with the camera we can see perfectly the posterize, because with the Spartan generator it's really difficult because it only has two colors. And in this one we can see perfectly how the change of the white of its color is how to say it, different, stretch a little bit. That's the main purpose of posterize. As we can see in the image, we have real time, completely real time. Like I was saying before, 60 frames per second with a resolution of 1920 by 1080. So perfectly. Well, we have a little lag, as I was telling. That is just because of the whole system, it's not because of the system created for the FPGA. And so, just like before, turn off the device and that's it. Now I'm going to change the demonstration by doing a fast filter, but using the VITA-2000 C that is connected with the module FMC Imagine by the SDI interface. There is serial digital interface, so we don't need anymore the SDMI. There is the cable of the SDI, so, and there's the camera. It's a really good camera with a camera lens. The problem is it doesn't have any features like the Sony does, like aim of the picture is like steady aim, for instance. Another problem with this camera is, as we can see, we are going to see in this demonstration, is that this camera doesn't have autofocus. It's a huge disadvantage. So first we have to start up the system, just like before. We have all set up and all plugged in. And this system is without the kernel for Linux. This is done with Beta Linux. It's developed by Xilinx, but it's quite exactly the same. But the problem is that this image is contracted and is compressed with all the system. We have the program for all the control of the system. We have also the kernel of the operating system. We have the video. We have everything inside. So it takes longer for decompress all the image. So it seems that it's starting right now, and just like before, we have everything exactly the same. So it starts of the driver of the, for instance, keyboard or the mouse. Here we can see how it starts the microprocessor. First, we cast the microprocessor, of course, and then it configures all the FPGA. Make the FPGA configuration, the system.bit, just like in any kind of card of FPGA. So as you can see, it takes longer than expected, so I have to cut a little bit the video, and here it starts all the system. So okay, just like in the other demonstrations, the system starts can start, for instance, with the command. So as you can see, here starts the test pattern generator, just like in the other demonstrations. And here is the image processing done by the microprocessor. So as you can see, there is the corners detected, and well, it's like a small blue for the edge. So we can see that the processing is by 1 frame per second. That is really slow. And as we can see, for the test pattern generator is 60 frames per second. So it overflows. And done by hardware acceleration is 60 frames per second. So as you can see, there isn't any kind of overflow. It's perfect real time. And now we use the camera for doing the image processing of the fast. Fast is an image processing that is more easy to administrate at the Harris. So as we can see here, in the keyboard or even in the car, it detects all the edges. Of course, this kind of image processing depends of the thresholds that you put it on the on this image processing. So here we have, just like in the test pattern generator, only 1 frame per second done by software processing, and 60 frames per second done by a hardware acceleration. So it's perfect real time. As we can see, if we focus and change the focus of the camera, it makes like a little wave for all over the keyboard. It's more smooth, or there's a kind of blur. So that is why I was saying that Sony cameras, for instance, the one that I use, the HDR-30V, is better than this conventional one, because it doesn't have steady aim, for instance, or autofocus. Even though we can see perfectly that it's done all the system perfectly, it's working quite fine. And this one is a video charged from the SD card. So because there is a bottleneck, of course, in the reading of the SD card, this one is reading by 6 frames per second. It's really slow. This is a huge video. It's not read and charged in the microprocessor, for instance, or in the memories. Is extracted and processed each image per demand. So that's the main problem. And this one is just done by the software processing. You can see it's even slower. It's 0 frames per second. That is because it's rounds, so it's maybe it's 0.7 frames per second, and it rounds to 0. And now if we put it by hardware acceleration, maybe it's not too clear, but we can see in the ears, or okay, now in the hands of the animal. This is 5 frames per second. The system is working in real time. The difference of 1 frame per second is because of the program for the measurement. So we turn off the card, and that's it for this demonstration. Now I wanted to put more footage of the fast hardware acceleration. This is also done with the Beta Linux, so we are entering the system by commands from the UART. So we have to get into the SD card and start the program for all the system to be charged in the operating system of Linux. I have also tried other kinds of filters, just like the median, the average filter, also a Cani. I extracted the code from the OpenCV's libraries and put in the pragmas or the directories for the hardware instructions. And I have to say that with this system, with the Zedboard or the 720 from Xilinx, there isn't any kind of problem with the hardware acceleration for image processing. So as we can see all in the image, there is, like in the previous videos, you can see perfectly in this kind of demonstration I put another light because of the quality of the camera, because with the other camera, the Sony HDR-30V, for example, with this kind of filter doesn't make any kind of problems with the focus or for example with exposure of light. It's a really good camera. It's designed for extreme sports, so has a really good quality of and resolution of image. Another good feature for this kind of system, the Zedboard or the Xilinx 720, is that it's all compact in the same microchip, in the same system on chip. It's like the system is a system on programmable chip, so the thing about it is in the same chip, so it is really easy to develop a new product, a new, for example, autopilot for UAVs or UGVs. So now I wanted to talk about the power consumption. It's a really important matter in this kind of systems, for example for UAVs, because you have to put in a battery for this system to work all the time. So I have implemented an easy tool that is available from Xilinx as a system implemented the VITA. A configuration that you can see from the UART, all the voltage, the current for every path of the system on programmable chip. And if we can notice, the maximum power consumption is 2 watts, so it's not too much for this kind of systems. The problem with this kind of demonstration, the one with the UART, the information given there, is that it's only for the system regarding for the microprocessor and all the control system, but not with the specification or configuration of the FPGA. That is because the controller of the access instrument implemented in the board is only measurement the inputs and outputs in this chip. So that is the reason I put the system .bit generated from the tools of Xilinx. With the Xpower, it's also a tool for Xilinx that it gives you like a briefery of all the consumptions. This information is only statistical, so it's depending, of course, of the system that you implemented, of the design, but it's only statistic. It's not a measurement in real time. So as we can see, this is a very viable project that can be implemented in a kind of system that needs a high or real-time processing image, and the consumption is not too big, so it could be powered with a battery. So hope you like it, and thanks for watching.